So, hi, I'm Micah. My cat Tuco is right over here, which is actually great. A lot of the time the stream starts up and he's just hanging out upstairs and sleeping or something. And this is the work in progress cat camera robot. You can actually just get right down here and hang out with him. Also here Tuco is climbing over all my stuff. Yeah, so what are some cool algorithms we can do that involve calculations based on neighbor frames? Like, obviously there's game of life. Like, it'd be cool to do something that's grayscale, like a flame simulation or something, like video feedback or fluid or something. Let's start with something relatively simple. Blur or diffusion kind of thing. By the time the next clock cycle rolls around, we should have the previous value for this pixel that we're currently working on in frame buffer out. I'm not going to have any kind of spatial diffusion, so I'm really just reading and writing the same location. But I want to see if we can do kind of a fade where maybe we set the pixel to white unconditionally when we're in the crosshair, but then otherwise we fade it slowly, and so the crosshair will leave a trail. I just noticed the block RAMs down here are now 27 out of 30, which is a good sign, because we were expecting to use most of the block RAM with this frame buffer. So the idea here is that now this kind of shader unit has a built-in frame buffer memory. That's this line here. All right, so this is generating a write signal for that memory. This is the memory address. This is the write signal. This is the data. Yeah, if it works right the first time, you usually did something wrong. That's often the case. Oh yeah! Frame buffer time. Oh yeah. Oh, we have time, 38 megahertz. I think this is bad grounding on my scope. The crosshair was also here just kind of for testing, and it might be cool to do something which can read its neighbors and maybe implement like a flame pattern or something. I want to see how many neighboring pixels I can read without running out of time. So I want this to wrap around on the 64 pixel boundary. I just don't know what to do with all these bits. Like, a lot of the old school effects that I would imagine just doing are grayscale or fundamentally grayscale, and then there's a lookup table. Like, one thing that would be kind of cool to do here is kind of an old school like flame or fluid simulation effect, which is a function that you can calculate for a particular pixel, knowing a small neighborhood of pixels in the previous frame. We only have one frame here. The line buffer is double buffered, but the frame buffer here I have only a single buffer. So what if we wanted to make kind of a blur effect that used the nearby pixels? Alright, so then this first clock cycle, that's where we have just the previous value of that pixel. I don't know, it's like I kind of want like weights for these, but we're dealing with integers here, so the weights that really make sense are 0, 1, 2, integers. Unless we made this fixed point and had a frame buffer which was deeper than 24 bits. I don't know if we need that though. Let's just do the saturation right here, maybe. So I'm dividing the components that I'm summing by 2 and then adding them. This will be like kind of a blur and attenuation if I did it right. I think we need to divide by 2 again. Guess I should keep the gain strictly under 1. Because it's multiplying by 5 here and dividing by 4 here. That's better. Yeah, now we're just kind of getting this like very subtle blur outward that does not oversaturate. We have time for some additional samples. We could add some corner samples. I was just imagining I kind of want the crosshair to be much less of a thing, but I also I want to replace that with something more interesting anyway. Let's just make it a dot right now, maybe. Huh. That was interesting at first, right? It was in like an iterative circle draw. So we're giving it more states. Let's give it more addresses. So here I'm generating addresses for all the neighbor pixels. Okay, so on cycles 0 through 8, we're setting up addresses for these pixels, and then on cycle 9, we are finishing on all the intermediate cycles. On every cycle except for 0, we want to be using that rsum output. So we're using it here, we're using it here. Okay, that's a little slower, but it still converges to white. Oh, right, because this is 9 now, and we're only dividing by 8. I could add a subtraction, I could multiply by... I mean, we have multiply and accumulate. I could just do it multiply. We haven't really had a lot of really great use cases for multipliers, but two things would be great for here are like any kind of brightness scaling, or like alpha blending, that kind of thing, or for generating coordinates for any kind of linear transformation. Wow. So we get an 8x8 or a 16x16 that go up to 50 megahertz. This is the internals. How do I want to use this then? I just want some kind of arbitrary pattern that'll help me see what else is going on here. Oh! That's a big improvement. Still not quite what I was looking for. I think my gain is still too low. Like, I want the video feedback to be a lot less subtle. It's nicer. I don't think it settles entirely to 0 now. And it's a little bit asymmetric. We can make this from the counter value, actually. Cool, so we can adjust the brightness to kind of get a good tipping point there. So this will indicate underflow, and then this is the non-underflow path. Yeah, like with these saturated add subs, like every bit depends on the carry chain. Oh yeah, we're not hitting 30 megahertz anymore. Is that going to be like the y coordinate maybe? So we might have to pipeline this a little bit, kind of break up this logic some more. So same thing, except we're doing this in a register now instead of in a wire. So we're taking an extra clock cycle to do this calculation. Place and route. So much placing, so much routing. Not quite fast enough. So we're just doing this increment and decrement one clock cycle earlier and storing the result temporarily. Oh, 37 megahertz. That was our hump to get over. Now the critical path is on the counter. Oh, the dither counter. I was having trouble kind of balancing it because either it would saturate to completely white or it would be so dim that the blurring was no longer showing up really. I need to do like 2 8x8 multiplies. So I could use 2 of those DSP units. Or sorry, 3 8x8 multiplies, so I could use 2 of the DSPs configured as 8x8s. So a DSP is not actually a processor. It is just the multiplication core, the multiplication and addition core. I don't know if the open source toolchain does that yet. This is a little more surefire, just instantiating the primitive directly. So I'm going to ignore the adder subtractor and just use this as a 2 input multiplier. Oh yeah, 8x8 power save turns off this register. So in this case, let's say I'm just trying to multiply fade amount by, say, RFB, GFB, BFB. So we're on this path, we're grabbing F and G. I want to turn these registers on. On every clock cycle, it multiplies fade amount times RFB and fade amount times GFB. So 1 clock cycle for the RAM, 1 clock cycle for the multiply. And then I think RFB fade, GFB fade end up on the right clock cycle for this stuff. Too slow. This looks like the saturating addition after the multiply, but I don't know what includes the multiply itself. So it looks like we got an upload. This might be glitchy because I don't think we're quite making timing. That's the munching pattern. It looks like it's being expanded such that every pixel is actually turning into a 3x3 neighborhood, which is also kind of fine. And then you're also seeing it wrap around because of that 3x3 neighborhood wrapping. So all of that is fine. The thing that is unexpected here is that it's acting like I am multiplying it by 1 instead of by 0.01 hex, I guess. 0 is unsigned and 1 is signed. I remember looking at this and seeing that it was opposite from that. Was I looking at a different document? Or did I just completely see the wrong thing? This looks much more like what I'm expecting. See, look at that fade. That's correct. Anyway, that is good. Let's add back my feedback that I was taking out to test this. Oh, that is just very dim. That's nice. So then at some point it saturates and we just end up with white. If I turn this down, I think there's a... Whoa. I wasn't expecting it to be quite such a steep cliff. Why is there just one LSB different between saturating completely and not really? I'd really like to know what this actual value is. 1, 2, 3, 4, 5, 17, 18, 19, 20, 9, 30. 1, 2. Okay, 32 it starts to saturate. This is 31. Still saturated. 30. So we're sampling these 9 locations. The results from the sampling, that goes right into this register, which is actually like these 3 registers, RFB, GFB, BFB. Those get multiplied by this fade amount. So that is still slightly higher than gain of 1. So what this is doing right now is it's kind of striking a balance in how much it's attenuating these values as it sums them together. So for every pixel in the frame buffer, it's taking a neighborhood of 3x3 pixels around that pixel. The pattern you're seeing is a little bit asymmetric because it's not double buffering. So the pixels do affect pixels that are further in, like in the future in that scan. So that's why it's a little bit asymmetric. Like I think you're seeing it kind of drift toward that way, mostly up, I think. So you're seeing that attenuation and blurring, and then the pattern that we're writing into the buffer before doing that blurring, you know, or in addition to that blurring, is this kind of munching squares. And the timer for the munching squares pattern is different for the red, green, and blue channels. I've shifted those over by 1 bit, so that's why you see the different munching squares kind of overlapping a little bit. All this munching feedback. Oh, can I set this to an initial value, maybe? Okay, the thing I was going to try to do is set a reset value for this, so it starts off with good parameters instead of without any feedback. That looks like what we wanted. And so the reset button now does not reset to 0, it resets to 30, but we can turn it down from there if we wanted. Oops. So we've got the LED driver from the last several streams, input counters, and then this is sort of our shader logic. So this is filling a buffer with pixels once per line, and then just kind of hanging out until the next line starts. That trace D7 on the scope, this one in red now, kind of pink, I guess. The wiggles on D7, each of those pulses are a pixel finishing. And then when it goes quiet in between in between rows, that's just where we have no more pixels to do, and we're still actually presenting the pixels we've seen so far. Oh, that's a nice view. And then we can affect kind of how much weight the feedback is given with the buttons. And so this is kind of a default value that's pretty stable, but we can turn this up and it makes it a little bit more kind of flowy up to the point where it actually just saturates. And then going down from the saturation point actually is not enough to keep it from resaturating immediately. You have to go down a couple of clicks and you can come back up. So yeah, just to explain what's going on the scope there, that trace D7 that's in red, that's coming from this renderer. So its job is to just keep the RAM double buffer full of pixels that the modulator can send out. And so it first gets the opportunity to send a buffer when the buffer swaps and a new buffer becomes available, which happens at the beginning of one row. So that's what's happening here. And then the data you're seeing at the bottom, that's actually a different row, not the one that's being rendered here, but the previous one that was rendered. It's that row being scanned out to the shift registers in the display, which actually happens a bunch of times per row. Yeah, no, 8 times, that's right. The shift register at the bottom that you see kind of shimmering on D0 through D6, that's handling 64 pixels at a time. But it does that for 2 pixels in parallel, whereas the renderer processes 1 pixel at a time. So the pulses on D7, if you counted those, you'd see 128 of those, I think. But they happen once per row, whereas on the bottom, those happen once per modulation cycle. And then that pulse on D3 is the beginning of the frame. It's a pretty nice pattern. I mean, it's not quite symmetric for the reasons I mentioned, but it looks good. And a lot of real-world problems have some sensible division between what kind of makes sense to go in software and what makes sense to go in hardware. But you can push that boundary a lot one way or the other. You can do stuff that a lot of people would do in software in hardware or vice versa. And for a design like this, I think what a lot of people would do with this is have the hardware manage the scan out. So generating those waveforms you see right there on the screen. That would be really well done by hardware and really, really hard to do in software reliably. A lot of people do it. Like, you can find libraries for like Raspberry Pi and Arduino that generate these waveforms in software, but they're usually not quite as stable as this and can't quite push the LED panel to its limits like this. So the FPGA is a great choice for generating the waveforms, and especially for the brightness control. Like this level of brightness control would be really hard to get without an FPGA, whereas this just makes it easy to push the panel to its limits. But then actually figuring out what to draw on it's kind of a challenge. So putting a CPU in here would be kind of nice. We could do a whole frame buffer kind of thing and, you know, write one frame, then have the CPU calculate the next frame. It turns out CPUs are actually pretty useful. Like, having the ability to use a series of instructions to program what a bunch of other units of hardware do on each clock cycle is a really handy building block to have. So while it's fun to do hardware without a CPU, which is what we're doing here, I think it might be fun on a stream soon to get back into doing system-on-chip stuff where there is a CPU involved. I could also see maybe modulating this parameter, because like you can get some interesting kind of swoopy shapes by temporarily kind of pushing it up into the high values, but then if it stays there for very long, it saturates really quickly. So like if we had an audio input or something, that might be one place to connect that. Alright, well, thanks so much for hanging out. This has been fun. I like the FPGA streams. I enjoy kind of starting from just like really low-level hardware and building up, but I also kind of like, you know, starting at an interesting place and looking up and looking down, since you're never really starting at the top or at the bottom. So, but yeah, thanks so much for hanging out. I'll see everyone next time. And a special thanks to everyone who sends in hardware, everyone who donates to the Patreon to keep this going. I do my best to try to put out content that folks find interesting and inspiring and educational and whatever else it can be. So always appreciate hearing about what works for you and what doesn't work for you, so I can keep trying to make the things that I produce more useful for people. What do you think, Tuco? It's just a robot watching you.